Got any questions, needs, concerns, etc. before we get started today? All right. Well, let's start today where we ended last time. Projector's on. Last time we looked at universal law of gravitation and how gravity can act as a centripetal force. I want to, in case I didn't make this abundantly clear or not, this type of question, I would call it an orbit question, and there's some on the homework, will be one on test 2, and there will be one on the final, which also means that there will be some on the practice test for those things as well. So to point out that this is a type of question that you will see again, where the force of gravity between two objects in space acts as a centripetal force. This would be any type of question where something orbits the Earth, like the moon or a satellite or a comet or something like that, or even the Earth orbiting the sun. Any situation like that, I would consider an orbit type question. And the main thing to remember for that type of question is gravity acts as a centripetal force, and that means you can set the formulas for those two things equal to one another. And you can actually use either version of the centripetal force formula, either the linear one or the angular one, just depending on what you know or what you're looking for. So this is something you'll see again, this situation, this kind of interaction between these two forces. So I wanted to highlight it. I recommend putting this on your notes and labeling it as such. We will continue practicing it. In fact, I actually want to, before moving on to the next thing, practice it one tiny little bit more. So we'll look at the orbit of a meteor around Earth instead of the moon. So, for an orbit question, gravity is going to act as a centripetal force, causing one object to move in a circle around the other because of the force of gravity drawing the second object towards the bigger one. We already did the moon orbiting the Earth, so now we're going to do a meteor orbiting the Earth. Meteor is going to have a mass of 500 kilograms, so about the size of a sedan, an average car, moving towards Earth. And its linear speed as it moves in a straight line through space is 7,650 meters per second. We would like to know what the orbital radius of that object will be as it approaches Earth and is caught by Earth's gravity. A lot of objects moving through space, if they move close enough to Earth, Earth's gravity will cause them to start bending towards Earth. Ideally, they'll either orbit the planet or possibly just bend slightly and then continue off in a straight line. But sometimes they are going to bend and fall onto the planet. And so scientists at NASA have to actually do this sort of calculation pretty frequently in order to figure out what height is something going to orbit at, is it going to orbit at all, is it just going to hit the ground? So we're kind of doing the sort of thing you might do if you worked at NASA. And we need to compare the force of gravity from Earth on the meteor to the needed centripetal force to make it orbit the planet, to try to figure out at what height, or rather what distance from Earth's core, it might possibly orbit at. Earth's gravity is going to act on the mass of the meteor. That gravity is based on the two objects' masses and how far apart they are. That goes on to inform what speed the meteor needs to be at to orbit at a specific distance. So what we're going to be searching for here is r. And it's actually the same r in every part of this. This r squared, this r, they all mean the same thing. It's the distance between the center of each object. So it's the same actual variable. It's not like the same letter for different things. So it's the same r in multiple places this time around. That's going to be a commonality in an orbit type question. Conveniently, the distance between centers of mass is the same as the orbital distance, the rotational radius. So r is what we're after here, and that's going to be the specific radius it rotates at based on the masses of both objects and the speed that it's moving at. Any questions about the basic premise before we start solving for r? All right, so for this thing to orbit, gravity has to act as a centripetal force. On the gravity side of things, we have almost everything on this side of the equation. First up in the formula is big G, which is always 6.67 times 10 to the negative 11th on your formula sheet. You never have to memorize that number. Next up is the mass of the two different objects multiplied together. Object one is the Earth itself, since Earth's gravity is what's going to cause this whole thing to happen. So, Earth's mass, listed there in the middle of the slide, is 5.98 times 10 to the 24th. And the meteor's mass is only 500 kilograms. So, pretty big size difference. Again, this meteor is about the mass of a car. So even if it does hit the Earth, we're not in extinction danger, thankfully. And then on the bottom, r is what we're looking for, so we're just going to leave that as r squared for right now. Any questions on the gravity side of this equation? All right. That gravity is going to act as a centripetal force. Centripetal force is equal to mass times centripetal acceleration. And there's two different versions of that formula. We know linear speed, so I'm going to recommend we use this version. So m times linear speed velocity squared over our unknown r. We do know that speed, thankfully. R is what we're looking for, so it's okay to leave it as is. Last question, though, is which of the two masses needs to go there?
Meteors.
Meteors, very good. And that is because why?
It is the object orbiting.
It is the object that is doing the potential orbiting. The centripetal acceleration, the centripetal force is causing centripetal acceleration in the meteor specifically, so it's the meteor's mass that goes here. Interestingly, we now actually have a 500 in the numerator of both sides. So the 500 can just kind of cancel out, which indirectly means that any object, regardless of mass, would need to move at the same speed to orbit at the same radius. It could be, the meteor in question could be the size of a car, a golf ball, or Alaska. It would need to move at the same speed to orbit at the same height above the ground. So meteor mass actually cancels out on both sides. And additionally to that, we also have r's on both sides. It's the same r, so what I would recommend we do is multiply r squared over to the right. That would make it r squared divided by r, and that just cancels out to r. I will show that though.
Or in the numerator.
Correct. So again, I'll demonstrate quickly. Multiply both sides by r squared. My least favorite part of these questions is just how big all the numbers are whenever I have to rewrite them between lines. I've noted that the 500s cancel out, so I'm just not going to write those again. So, multiplying both sides by r squared, that's going to fully cancel it out on the left. Then on the right, we've got number divided by r times r squared over r. We'll simplify to just r. So it's very good that it's the same radius. We get some interesting canceling shenanigans. And it's still the same radius if you use the angular version. It's just you'd end up multiplying the r squared over and you'd end up with r cubed. So they combine somehow, whichever version you use. And we want r by itself. that would be big G times Earth mass divided by linear velocity squared. If you input everything correctly into your calculator, please let me know if your math disagrees. That should give us 6,815,600 approximately meters. And this is the distance between the meteor and the center of the Earth. This is not its height above the ground. This is the distance between the meteor and the center of the Earth. Since the center of the Earth is the center of Earth's gravitational effect, and since that is the point that the meteor would orbit around, is the center of the planet. So, if I was to try to make a scale picture here, that is what R means. And additionally, just to compare, that would convert to about 6,800-ish kilometers, which I would like to briefly compare to the Earth's radius of 6,380-ish kilometers. Note that R is bigger, which means that the object does actually orbit above the ground, which is good, because if that R was smaller than the physical size of the planet, that would imply that the meteor is trying to orbit within the planet, which just means it hits the planet. And if it did hit the planet, a 500 kilogram meteor is not going to, dinosaur us, thankfully. In fact, it might burn up on entry and it might not hit the ground at all. But we've proven that it will orbit at, like 450 kilometers in the air, which, again, not gonna hit the planet, that's good. The problem is that that's the height of the space station. So it'd be a problem for them. Or it could be a problem for them. Yeah, the space station's something like 400 kilometers above the ground, as it turns out. Very close. So, how does this feel? All right. Again, main thing that you should keep in mind, this is an orbit type question, so this is the main approach for anything orbiting anything else in space, where gravity is the thing acting as the centrifugal force. For any other Earth-based problem, any number of forces could serve as centrifugal force, but if it's orbiting in space, it's going to be gravity specifically, and that means you can have some interesting interactions between the two formulas. Yes?
So whenever you ask this question on a test, it's going to be from Earth's surface, not from Earth's center.
Well,
when you ask for where is its position, or will you state that in the question?
I will state in the question. I will make it clear what I'm asking for. Note again that the R's in this formula are from the center of the Earth to the object, and in all likelihood, that's just what I'm going to ask you for. Either I will tell you that distance, or that is what I will ask you for, meaning that this is your final answer and you're done. Especially since on a test, I don't want to trick you. I just want to see what you know in an hour. I only asked this other question just to point out it's from the center of the Earth, it's not from Earth's surface. So if I specifically say orbital radius, that's what R is, and that means once you get here, you're done. Does that make sense?
Yeah.
Okay. I will usually say the words orbital radius. That is what I want. Homework might get weird about it sometimes, but on a test, I don't want to trick you. I will tell you exactly what I mean and what I want. Anything else on your minds for right now? All right. So this is just a little bit of review from the last thing we talked about. The main thing that I actually want to do today is begin chapter 8, which I don't mean to sound scary, it's just more rotation stuff. It's just rotation week number 2, basically. But it's important to start now because the first concept in this new week is torque, and this week's lab is a torque lab. So we're going to go over all the materials that you would need to do lab this week, especially if you have it today or tomorrow. So any objections before moving on to that? All right. So, chapter 8 as a whole, again, is really just rotation part 2. What we did last week was what I would call the basics of describing rotational motion. We looked at how we describe, rotational displacement, velocity, acceleration, how those relate back to their linear counterparts, how we use them to describe rotation along with centrifugal force. This week, we're going to be applying that information to some more advanced topics. But the weird thing about the topics from this week is that they're the same topics we've already talked about. If you recall, we began the semester looking at displacement, velocity, and acceleration, and then we spent all the months up till now looking at all the various concepts related to those things. Force causes acceleration, momentum involves velocity, kinetic energy involves velocity, all those concepts tied into each other, and we can use all of these things to describe linear motion. And kind of like how displacement, velocity, and acceleration all have angular counterparts, every single way that we describe linear motion also has an angular counterpart. There's an angular counterpart to force, to momentum, to kinetic energy, and weirdly also to mass. We'll talk about that one later. So this week we'll be looking at these additional angular concepts, just comparing them back to their linear counterparts the same way we did last week. The one we're going to focus on today is torque. Who's heard that word before?
Yes.
Okay. When I was a kid, I think I heard it most often in like car commercials, talking about the torque the engine exerts on the tires and things like that. And this is actually one of those physics concepts that I find people have a pretty good subconscious understanding of, because it turns out you have used it every single day of your life ever since you started walking and picking things up with your hands. So again, good conceptual understanding, subconsciously, we're just going to spend today putting words and numbers to it. So the word itself is torque, T-O-R-Q-U-E. And torque is the angular counterpart to force. The formula that we're starting with for torque, this is the variable for it. This letter is technically a lowercase Greek tau. That letter is usually spelled T-A-U. So the letter tau refers to torque in physics. Tau is kind of a weird one because it's basically T, but it's like they're using a different font. This is uppercase tau, which is reserved for its own specific thing in physics. Lowercase tau, which is torque. Uppercase t, also its own separate concept in physics. And lowercase t, which is time. So all 4 of these letters mean something different in physics class. That's not confusing. But torque is specifically lowercase tau. I emphasize the weirdness of it to make sure it is distinct from T in my handwriting. Some computers will put this little swivel on the top there. I think it looks like a weird hat or like it's dancing or something. But when I say tau, I'm referring to this new concept of torque. And this formula says that torque is a vector equal to radius times force.
It's a multiplication.
Yes, it's multiplication, sorry. This symbol is perpendicular. It's meaning, I'll talk about this in a second, how the radius and the force need to be perpendicular to each other, but it is radius times force, sorry. If I don't add a specific symbol, if their letters are just next to each other, you can assume multiplication.
Oh, that's not an underline, that's actually like a perpendicular symbol.
Yeah, like each letter is underlined, I'll admit, but there is separately a perpendicular symbol between the R and the F.
Gotcha.
So you know what, let me rewrite it. Torque equals radius, and the radius is a subscript attached, sorry, perpendicular is a subscript attached to radius. Radius is being multiplied by force. Is that how it's written on the formula sheet? No, the formula sheet does it that way. You can add a little multiplication symbol in there if you want. So, well, first, questions about anything I've said up until this point. I now plan to further describe torque. Okay, so the definition, torque is the angular counterpart to force. What I mean by that is, force is known to cause linear acceleration. If you push something, it's going to start moving in a straight line, correct? Force points in a straight line, acceleration points in a straight line. Bless you to whoever sneezed. Torque is very similar, except replace all the straight lines with rotation. There's two formulas for torque. We're going to focus mostly on this one for right now, but I want to at least acknowledge the second one. Because this formula says that torque causes angular acceleration like how force causes linear acceleration. This is the purpose of torque. Linear force makes things move in straight lines. Torque causes things to spin. If something is spinning, it's because torque acted on it to make it spin. To clarify, I will direct your attention again to the disembodied bike tire of science. There's loads of different ways I can exert force on this thing. Up till now, well no I haven't. Rewind. I can exert force on this tire in a number of different ways. First, if I exert all of my force directly on the axle of the wheel, note that it doesn't really spin as a result of that. If I'm exerting linear force directly on the center of mass of the object, it just linearly accelerates. This isn't rotation. This is just F and A. Something changes though if I exert the force on a different spot of the tire, namely if I grab the edge of it. If I grab the edge of the wheel, note that this spot that I'm holding is a distance away from the fulcrum that I was previously acting on. And so that is the R in the formula. It's the physical radius away from the axis of rotation. And if I exert force here, now it spins. Again, different to if I exert the force here. When you exert force some distance away from a pivot point, you generate torque. And that torque causes it to spin rather than move in a straight line. And you have done this every day of your life since you started walking and using your hands. I can almost guarantee that, if for no other reason than because of these things. I'm just literally pointing at the door right now. This object is just designed to use torque to open and close. I know this because the physical object has an axis of rotation, the hinges, and if you were to come up and try to open or close this door, where would you put your hand on it to apply force?
Furthest spot away from the point of torque.
Furthest spot away from the hinges, and that's why the doorknob is over here and not over here. If the doorknob was here, we'd have a bad time. Doorknob is over here because this entire edge is all about as far away from the hinges as it can get. And even if the knob wasn't there, you conceptually know from experience that you put your hand on this side of it. Sound familiar? And again, that's because this edge has the biggest possible radius away from the hinges, and so grabbing it there will generate the most amount of torque for the force you put on it. I challenge you to, move a door around, feel how much force that takes you, and then try to apply the same amount of force here. And it won't go nearly as smoothly. Here the radius is teeny tiny, and it's taking me a lot more effort to even get it to budge. It won't budge at all if I act directly on the hinge. This will never make the door spin. And that's because now the radius of force compared to the hinge is just 0. So this will never generate torque. This will never cause rotation. I need to act a radius away to cause rotation and actually make the door open. Every day of your life. Wheels use it too, and that's not even if you're just using your hands on it, because for this thing to spin, if I'm exerting a force on the axle of the wheel, that alone won't cause it to rotate. So note that if it's not touching the ground, this doesn't cause rotation. But if it's touching the ground, and I exert force on the axle to move the wheel forwards, friction from the ground actually acts a distance away from the axle, and that will cause rotation. Lastly, the other most common place torque pops up is in pretty much every tool that humans have ever invented that is meant to be used by your hands, like wrenches. The entire purpose of a wrench is to make a bolt spin, right? Now, have you ever tried to tighten or loosen a bolt with your bare fingers? Is it fun? No. That's because if I physically grab this, just my bare hands, the best radius of rotation I can get is just the radius of the physical bolt. And that's like, on an actual bolt, like a millimeter. That's not a lot of torque. So you have to use a lot of force to try to do that with your bare fingers. The wrench, though, has a handle, and in this case, I've comically made it 1 meter long. So if you exert 12 newtons of force on the end of the wrench, again, 1 meter long, how much torque do you make? 12. 12 watts. What is the unit for torque?
Newtons per meters.
Newtons times meters. It's not newtons per meter, it's newtons times meters. It is admittedly a weird unit. A lot of people just say Newton meters. But that just comes from the formula. It's physically newtons times meters. So they didn't give it a unique one, but at least the one they gave it kind of makes sense. But note that it isn't per meter, it's just times meters. So yeah, 12 times 1 is 1 newton meter of torque. And that is way more than if I just put 12 newtons of force directly on the bolt with my bare hands. That would be like 12 times 1 centimeter, which would be 0.12 newton meters. So not nearly as effective. Furthermore, let's say that I had a wrench that was twice as long. So same force, but 2 meter long wrench. How much torque do you get? 24. So same amount of force, same amount of effort from your own arms, but double the effect. Twice the torque means twice the angular acceleration. Again, slightly different formula, but just to kind of skip ahead slightly, you double the torque, you double the acceleration. It spins twice as fast. Or it's easier to get moving at least. And pretty much most tools that humans have made to use with your hands uses this somehow. It's not just wrenches, screwdrivers and hammers involve it too, because swinging a hammer does involve rotation, and note that the end of the hammer is a distance away from your hand, so you make more torque and get more benefit using the hammer than just punching the nail, which again, I don't recommend. Screwdrivers too, actually, because the length of the screwdriver, even if you're spinning the screwdriver, does still generate torque. And even outside of just tools, well, another tool would be a crowbar. I'm going to point out crowbars before I move on, because if you've ever tried to lift a manhole cover directly, it probably hasn't worked. But if you jimmy a crowbar down there, generate torque, the manhole cover will rotate out of the way, and then you can just slide it off rather than deadlifting it. And the longer the crowbar, the easier that job is. It's not just tools though, because this also applies to baseball bats, tennis rackets, golf clubs, swords, axes, pretty much anything with a handle. Baseball specifically, again, using the bat radius, you generate torque, and you get a lot more bang for your buck than if you just try to punch the ball out of the air. I know from experience, because in volleyball, I panicked in high school and just punched it, and that didn't work all that great. I know there's no bat in volleyball, but punching the ball doesn't work well. So, torque is everywhere, literally. You can't avoid it, as it turns out. Conceptually, how are we feeling? Digging up those core memories? All right. Now, there's a couple tricks to torque that I want to point out, since lab this week involves it. So, some things I want to make sure you're aware of. There is that perpendicular symbol there, and it means that the force does need to be perpendicular to the radius. Looking at the bike wheel again, note that to make this spin, if I'm physically holding it here, this point is horizontally a distance away from the axle. And if you grab it here, what direction do you think to move your hand in to make it spin?
Down, up.
Down, or alternatively up. Both directions are perpendicular to that horizontal radius from where I was grabbing it. If I tried to exert a parallel force, that would be either right, which doesn't cause spin, just causes me to pull it this way, or left, same thing, doesn't cause spin. The force had to be perpendicular to the radius to actually accomplish anything. Same is true with the door. Because to make it spin, you grab it and then you either pull towards you or away from you, not in the same axis as the door. This does nothing other than make me look silly. So, the radius and the force must be perpendicular, which can cause some weirdness if the force isn't totally perpendicular, because you or someone you know might have at some point gotten really frustrated with a wrench, pulled it in kind of a suboptimal direction. Like, say I need to make it turn this way, I just grab it and I pull towards me, and perpendicular force would point this way, but I physically can't pull that off from this angle. I just kind of have to pull down towards myself, and that's not the ideal angle. For that reason, even if it's the same 12 newtons and the same 1 meter long wrench, not all 12 of those newtons are perpendicular, which means, trig again. Gotta use a tiny bit of trig to figure out how much of those 12 newtons are perpendicular. If that's 50 degrees, drawing's not really to scale. If that's 50 degrees, sine of 50 equals perpendicular leg over the hypotenuse. Only about 9.19 of the 12 newtons are perpendicular, and so that is the amount of force that would go in the formula. So instead of 12 times 1, it's 9.19 times 1, and the amount of torque I produce is lessened for no other reason than the angle is wrong. So, there is actually, turns out, a tiny amount of trig in the later half of the class. So just remember that that perpendicular symbol in the formula is not just for show. You have to at least think about it. I will, admittedly, most of the examples I bring up are perpendicular as much as possible, but it's worth considering because sometimes, again, you can't really avoid it in reality. Sometimes the angle's just gonna be wrong or non-ideal. Any questions about this concept or the mathematical trigonometric implications? All right. The other quirk I'd like to bring up, and the main one that will tie in the lab this week, is how net torque can work. Specifically when net torque equals 0. If you'll recall, linear forces, if a bunch of different forces are all acting on the same object, they all add together to contribute to the net force, and the net force is what causes net acceleration. Sound familiar? Now forces can point in a bunch of different directions, and therefore so can linear acceleration. Torque is similar, because net angular acceleration is caused by net torque. There can be more than one thing generating torque on the same object. For example, if this was a car tire, the engine is going to exert torque to try to make the wheel spin this way, but friction is going to try to exert backwards pointing force to slow it down. That would be two different torques, and only the net torque would end up contributing to the spin. So multiple torques can act on the same object at once, and they all have to add together, like force, to create net torque, and net torque determines net angular acceleration. Does that analogy feel good so far? All right, now the main difference between the two, well, first of all, we call this, rewind slightly, we call this rotational equilibrium. This is just linear equilibrium. This is rotational equilibrium. Net torque has to be 0 for an object to not be angularly accelerating. So basically, if something isn't spinning, net torque on it must be 0. That's true for the wheel and the door sitting still. Technically true for anything that just isn't spinning. And most things aren't spinning. Now, the weird thing with torque is still a vector. Technically, so is angular displacement, velocity, and acceleration. They are all still vectors, but unlike force that can point in any possible conceivable 3D direction, torque only has two directions that it can really point in based on your perspective. Those being clockwise and counterclockwise. Those are the only two directions something can spin in, right? So torque really only has the two directions to worry about. So unlike force, where you would have to keep track of, say, positive and negative in multiple different axes, torque only really has the one axis, and you have to consider whether a certain torque is trying to make it spin clockwise or counterclockwise. And for net torque to equal 0, all of the clockwise torques have to cancel out all of the counterclockwise torques. So this is still basically true. Net torque must equal 0. You have to pick if counterclockwise is positive or if clockwise is positive. But equally true, sort of another way of describing it, is that the net counterclockwise torque must equal the net clockwise torque. They have to equal each other and cancel out, such that if you put them both on the same side, subtract one from the other, they equal 0. So this has to be true for any object that is not rotating, or alternatively is rotating at constant velocity. And main place you're going to be seeing that in lab this week is seesaws. Because as it turns out, this piece of children's playground equipment is once again just applied torque. Can't really escape it. Now when I was a kid, me and my cousins would all play a game of trying to keep this seesaw as level as possible. Every kid would sit in a different position. Since I was usually the biggest kid, I would stand on the middle, shifting my weight to try to balance the thing. Please tell me I'm not the only person in the room that tried to do something like that. Okay, well, at least you guys are smiling. So, I made a game of trying to balance the seesaw. We are going to do math about a balanced seesaw, both right now and also in lab this week. Now, lab is not going to involve physical teeter-totters, sorry to say. Lab this week, you're going to build teeter-totters out of meter sticks and try to level them based on what objects you have hanging from either side. So, not full-size ones, but the principle still applies. Now, in this case, we've got two different kids sitting at two different positions on the teeter-totter, and they're playing the same game I did. They want this thing to be level. They don't want it to rotate. They want to keep it as still as they can. And for this thing to be level, all the torques on it have to add up to 0, and that means all of the counterclockwise torques have to equal all of the clockwise torques. And because the two different kids are sitting on two different sides, one of them is going to generate counterclockwise torque. Note that the weight from kid 1 is going to pull down on this side, and that would have the effect of making it spin counterclockwise if imbalanced. Meanwhile, the kid on the right, their weight also points down, but because they're on the other side of the fulcrum, that would make it spin clockwise. So the same direction of force can generate opposite torque if it's on the other side of the fulcrum. That's why I tend to think about it in terms of clockwise, counterclockwise, rather than the direction of the force. Think about it in terms of the direction of the torque the force is going to generate. So even though the forces, the weights of the two kids point in the same direction, they're each going to generate opposite torque from one another. And if they want the seesaw to be level, they both have to generate the same amount of opposite torque. And since they weigh different amounts, they're going to need to sit in different positions to make that happen. And so that's just what we're going to prove mathematically here. We're going to figure out where kid 1 has to sit such that they negate the torque that kid 2 creates. Because they can't change their masses, but they can change where they sit. And again, lab this week will be similar. You're going to physically build teeter-totters out of meter sticks. You're going to hang mass from one side of it and figure out where a different amount of mass has to go on the other side. Does that sound fair so far? All right. Now in this case, the torques have to equal each other. And I like to describe this, as I showed on the previous slide, as net torque counterclockwise must equal net torque clockwise. I like to set it up like this because my brain is very visually based, and this lets me physically put left kid on the left and right kid on the right. You could do this though, like we do with normal forces, where it's just net torque equals 0. You just have to decide, is clockwise negative or is counterclockwise negative? Because they do have to oppose one another. Looking at it from this perspective, left kid is making the counterclockwise torque, because again, if you ever need to physically look at something to figure that out, note this kid, force is going to point down. If you physically imagine grabbing the teeter-totter and pushing it in that direction and keep going, you'll note counterclockwise. So the torque from kid 1 is creating the only counterclockwise torque here. So kid 1's radius times kid 1's force. And that is set opposed to the torque that kid 2 is creating. Note their weight does still point down, but because they're on the other side of the teeter-totter, if I physically tried to grab the teeter-totter and move it in that direction and kept going, that's clockwise. So on the clockwise side, we just have kid 2. So just the one torque generated by kid 2. They each have different masses, so they both have different forces that they're exerting. So they're going to sit at different distances. We're just going to quickly prove where kid 1 needs to sit such that they equal each other. Now, based on the masses, you might have already guessed, but I still need to prove it. So, any questions about how this is set up so far? All right. On kid 1's side, we've got kid 1's radius times kid 1's weight. Kid 1's radius is currently unknown, but we can figure out their weight since we know their mass. So just 30 kilograms times negative 9.8. On the other side, we do know kid 2's radius, and we know their mass, so we can also find their weight. Note that the negative 9.8 both just kind of cancel out, which gets rid of the negatives, which is nice. Factoring in that these cancel out, I would say that the next line down is going to be R1 times 30 equals 1 times 60, which is just 60. Therefore, R1 is going to be 60 over 30, or 2 meters. So, kid 1 has half as much mass. They have to sit twice as far away to generate the same amount of torque. How's that feel? All right. Again, lab this week is very similar to math, so make sure to bring these notes. I'll go ahead and point out that, hello, come on. Some of the lab problems will have more than 2 masses. Say there was a third kid who was also sitting on the left. Their weight would also create a counterclockwise torque, which means that the sum of the counterclockwise torques, there would be physically another torque added into that left side. So it's not always going to be one against the other. Sometimes there's 2 things working together to both generate torque in the same direction. Questions, concerns? Inquiries, haiku. All right, if you guys need anything, you can bring these notes to the lab and have a nice day. Yes.